We are beginning the study of integration, which will make use of antiderivatives, although not quite yet. We're going to build up to it from a historical perspective, which means we're going to be taking the long way around to get to definite and indefinite integrals. So we're embarking on integral calculus, and remember that at the beginning I talked about, and your textbook talks about, how there are these two main branches, differential and integral calculus. So most of the semester we spent on differential calculus. And now we embark on integral calculus. And the interesting thing about these two, as I mentioned way back, is that they were actually created by two different people at two different times, but they turn out to be related in a very interesting way. One of the reasons why integral calculus was developed was to solve this thing called the area problem. The area under a curve represents a total change in something. So how do we find the area of the curve between the curve and the x-axis? It's not any geometric form that we have a formula for. So the first thing was that a method was developed whereby you would draw rectangles, fill up the space with rectangles, make sure that the widths of the rectangles were all equal. That made calculation a little bit easier. But fill up the area with rectangles, add up the areas of each one of those rectangles, and then you'll have an approximation of the area under the curve. And you can see already that this is a pretty coarse approximation. There was also the distance problem, which turns into the area problem. If you look at this particular problem, the speed of a runner increased steadily during the first 3 seconds of a race. So somebody clocked her speed at half-second intervals, and the question is, what is the distance that she traveled? If you remember, distance is equal to velocity times time, but only if velocity remains constant over time. And we have a velocity that is continually changing. So at each half-second interval, we can take the time and multiply it by the velocity to get the distance for that half-second interval. So we have to do that for each half-second interval and add them all up to get the final distance. And if you plot the curve, time versus velocity, it turns out that the area under that velocity curve is the total distance that this runner ran during those 3 seconds. So the distance problem turns into the area problem. Now there's a fine art of drawing rectangles. You can position them in different ways. At the left-hand picture, you'll see we're positioning by left-hand endpoint. So that means you take the left-hand corner of the rectangle and you draw it up to the curve, and that fixes the height of that particular rectangle. The right-hand graph shows rectangles shown using the right-hand endpoint method. So you take the right-hand corner of a rectangle, draw the rectangle up till it meets the curve, and use that as the height for that particular rectangle. And of course, you use the same method for every rectangle in that particular graph, either the left or the right. And if you look at it visually, you'll probably see that the area under the curve is somewhere between the two approximations, one using the left-hand endpoint and the other using the right-hand endpoint method. Now, you don't have to stick to the left-hand or the right-hand endpoint. You could center the rectangle so that the middle of the rectangle is drawn up to meet the curve, and that fixes the height of the rectangle. And it doesn't have to be the midpoint. It can be anywhere along the rectangle as long as you're consistent about how you do it for all the rectangles. Does this look tedious? It kind of is, but we're building up to the calculus of it. So if we start simple, doing one calculation, and this time we're going to use a curve where we actually know the function of the curve. And many times we won't know that function. So we're going to divide this interval into two pieces. So we're just going to use two rectangles, and we're going to use the left-hand endpoint. So you can see how those rectangles are drawn. We're going to get the area of each rectangle. So rectangle 1, its height is 2, and the width of each rectangle is 1, because remember, we want equal widths. And if our interval is going from 0 to 2, we're just dividing that in 2 to get the width of each rectangle. For the second rectangle, we take that left-hand corner, and it is 1 by square root of 3. So we actually had to use our function at x is equal to 1 to calculate the height of that rectangle. At any rate, now we can take the area of the rectangles, we can add those areas together, and we come up with an area of 3.73. And we can see clearly from the visual that's pretty well overestimated. Now if we do the same thing with the right-hand endpoints, turns out we can only draw one rectangle. We're going to take the right-hand endpoint and draw that up to the curve. So that first rectangle has dimensions 1 by square root of 3. But then when we go to the right-hand corner of the second rectangle, the curve is already down at the axis, so there is no rectangle. F of 2 is 0. So the area of rectangle 1 is square root of 3, and the area of rectangle 2 is 0. Add those together and we get 1.73 square units. So we have what we could call an upper bound, and we could call the right-hand endpoint the lower bound. And so if we average those two together, we might get a closer approximation of the area. But how do we get better estimates? I mean, none of those methods, the right, the left, the average, they didn't really look like they'd be great estimators. Well, the trick is more rectangles, better estimates. And now how are we going to do that? Are we going to tediously draw 10 or 100 or 1,000 or 1,000,000 rectangles and go through and calculate each area and then add them up? No, we hope we're not going to do that by hand. We're going to use calculus.